Hi everyone. Today in this video we're going to talk about the Koopman operator and how we can use it to analyze nonlinear differential equations. And in some cases we find very interesting results that a nonlinear ordinary differential equation can actually be simulated using a higher dimensional linear dynamical system on observable functions of our state variable. And we're going to show that in some cases, some limited cases, you can actually use this to develop nonlinear optimal control laws, which is really exciting. This is joint work with Brunton, Josh Proctor, and Nathan Kutz. So the Koopman operator has been around for quite some time. Koopman in 1931, in the Proceedings of the National Academy of Sciences, put forward this paper, Hamiltonian Systems and Transformations in Hilbert Space. And in this work, he outlined how you can think of finite dimensional but nonlinear differential equations as, in terms of this Koopman operator, which is an infinite dimensional linear operator that acts on the space of all possible observable functions of our state, the state of the ordinary differential equation. And this operator theoretic perspective is very appealing in some sense, that instead of having these nonlinear differential equations with chaos and all kinds of the associated troubles, now we have a linear operator on the Hilbert space of observable functions. But the trade-off is that this is now an infinite dimensional linear operator with all of the associated difficulties. So recently, Igor Mezich has been looking at how you can think about data-driven dynamical systems in terms of this Koopman framework. And in the last 10 years or so, there's been a lot of interest around using Koopman operators to study nonlinear dynamical systems, to simulate approximate systems for control and things like that. In 2009 and 2010, there was a strong connection made between the Koopman operator theory for nonlinear dynamical systems and experimental data from fluid mechanics, which really created a lot of interest in this Koopman operator framework. And if you want to read more about this, there's a couple of great review papers that you can read a lot more about Koopman analysis, the history, the applications, and some of the implications of this infinite dimensional linear operator for dynamical systems. So today we're going to talk about when you can really use this infinite dimensional linear operator and when you can obtain finite dimensional approximations on an observable subspace that are exact. Okay, so a little bit of overview about the Koopman operator. We have some dynamical system, x dot equals f of x. We consider x to be the state of the system. This could be a very high dimensional vector of fluid velocities at a bunch of point locations, or it could be the position and velocities of all of the planets in the solar system. Lots of examples, right? This could be the angle and velocity of a pendulum, right? So you have some dynamical system. Generally, we're interested in nonlinear dynamics that are a little more rich and interesting in describing physical systems. And anytime you have a continuous time differential equation like this, you can always represent it as a discrete time update in terms of this flow map operator. So if I have some position x at time 0, I call this x naught, then I can integrate that initial state through my velocity field f of x to some point later at time t naught plus t. So this is the time t flow map that advances states forward according to this dynamical system. And either of these perspectives is totally valid. I like to think about continuous time differential equations sometimes. Other times I think about discrete time dynamical systems. So for example, when I'm collecting experimental data from measurements at discrete times, I might think about that as a discrete time dynamical system. And the Koopman operator is this beautiful operator. It's an infinite dimensional linear operator that operates on the Hilbert space of observable functions g on our state x. So let's break this down a little bit. We have a state space x. X is just, it lives in some vector space or some manifold. And there's the Hilbert space of all possible observations I could make about that state. I could just measure the state. I could measure the components of x. Those would be kind of linear measurements. I could measure x squared or sine of x or all kinds of measurements I could take of my state. And those measurements are given by these functions g. and they form an infinite dimensional Hilbert space. So what Koopman realized, and this is a really important realization, is that we can define an operator, this K sub t operator, this Koopman operator, so that the way that it acts on observable functions is to return that same observable composed with my flow map, my time t flow map. And what this means is that if I take the Koopman operator applied to an observation at time k, at time k, what I get back is that same observable function, my same measurement, applied to the flow map of xk, which is my measurement at the next time step k plus 1. So this is very powerful. This says that I have a linear infinite dimensional operator k so that it tells me what my measurement will be at the next time. So it's a linear way of advancing my observable functions forward in time, which is really cool. So it's a discrete time update on my observable functions. But again, these observable functions live in an infinite dimensional Hilbert space, and so k might actually be quite complicated. Now, there is a continuous time version of this Koopman framework, so we could say that the time derivative of my observable function is this continuous k times my observable function, where this is the infinitesimal generator of this one parameter family group. So this is kind of the Koopman framework. We trade the nonlinear, kind of rich chaotic dynamics up here on a finite dimensional state space for linear but infinite dimensional dynamics on this Hilbert space of observable functions. And I want to just draw this as kind of a cartoon to get us thinking about what we might want to use this Koopman operator for. So here we have some manifold where our dynamical system, our state, lives. This might be the fluid velocity field evolving in time for flow past a wing, or this might be the position of all of the planets moving around. This is just the dynamical system on whatever constraint manifold I happen to live on. And each of these states is advanced by this flow map f sub t. And this is a nonlinear flow map. So if I have some observable functions, maybe I measure just the coordinates of x, or I measure x1 squared, and then I measure x2 times x3, and I measure a number of observable functions, so that's this vector value g, then I essentially get out these m measurements in these y directions, in this m-dimensional vector space. And so if I can advance my state using this f flow map, then I want to be able to advance my measurements y using some finite dimensional approximation to my infinite dimensional Koopman operator, which I'm calling bold k. And so the only way that you can do this is if you have what's called a Koopman invariant subspace of observables. Okay? So if I have in my observable Hilbert space, there are some eigenobservable functions of my Koopman operator, and those eigenobservable functions always span a Koopman invariant subspace. So that if I have some observable function g that is written as a linear combination of these eigenfunctions, when I hit that measurement with my Koopman operator, it stays in that subspace spanned by those eigenobservables. And so you can always take measurements which are eigenobservables of the Koopman operator, and you can define a finite dimensional subspace of your observable Hilbert space, where your Koopman operator restricted to that subspace is just an m by m matrix, which is really cool. Now the drawback to this is that you can't always easily find these Koopman eigenobservables. So it's not always clear from the dynamical system how to find the eigenobservables of this operator and how to define these Koopman invariant subspaces where I can get finite dimensional linear models for my dynamical system. Moreover, for lots of applications, we would love for our observable subspace to also include measurements of the state itself. So if we're going to do control, we might be penalizing the deviation of this state from some nominal value. And so we would want our Koopman invariant observable subspace to also include the state dimensions themselves, these x variables. And what we're going to show is that that's a pretty restrictive thing to ask, and there's only some dynamical systems that admit these Koopman invariant subspaces of finite dimension that also include these state variables. But when we do have them, you can do amazing things with nonlinear controllers that I'll show you about in a minute. Okay, so this is an example that's really great to illustrate the power of this Koopman framework. And I'll just kind of walk you through it. So we have a nonlinear differential equation in two state variables, x1 and x2. So x1 dot equals mu x means that x is either attracting or repelling, depending on the sign of mu. And x2 dot equals lambda times x2 minus x1 squared. The idea here is that if lambda is kind of a fast attracting eigenvalue, then x2 is going to adhere onto a manifold given by x2 equals x1 squared very quickly. That's what's shown here in this red dashed parabola. So here I have three initial conditions, and I'm showing you the integration as I run these initial conditions through the system for a stable mu and a faster stable lambda. So you see that rapidly these trajectories kind of come up to the manifold, and then they slowly follow this manifold down to the fixed point at 0, 0. Okay, so this is a simple dynamical system. It's got an isolated single fixed point. We know lots about this system. We can simulate it, in MATLAB using OD45, no problem. But what I'm going to show you is that with this Koopman framework, you can essentially represent these nonlinear dynamics using a linear differential equation, but on a higher dimensional space defined by these observable functions. Okay? So what we're doing here is we're going to assume that we have some new coordinates, y1, y2, and y3, and that they're given by our original two coordinates, x1 and x2, but also by this new nonlinear observation of x1 squared. And in these new three coordinates, y1, y2, y3, we can write down our differential equation this way. So the first two rows of these y dot equations are my original dynamics. Okay, y1 dot equals mu times y1. That's just another way of saying x1 dot equals mu times x1. y2 dot equals lambda times y2 minus lambda times y3. That's another way of saying x2 dot equals lambda x2 minus lambda x1 squared, because that's what y3 is. And then you can take and you can actually write down this ddt of y3, and we're defining y3 to be x1 squared. So this is ddt of x1 squared. And if we just apply the chain rule, we get 2 times x1 dot. Okay, and if we plug in x1 dot from up here, we find that this is 2 mu x1 squared. And lo and behold, that is 2 mu y3. So even this new nonlinear function y3 equals x1 squared can be represented linearly in terms of this new set of observables. Okay? And here what I'm showing you is a three-dimensional plot of these trajectories for this Koopman linear system. This is an honest-to-goodness linear system, right? There's no nonlinear terms here. It's written in terms of these observable functions, which are nonlinear in x. And if I follow these white trajectories in this, this three-dimensional Koopman linear system, and I follow what happens to these first two coordinates, I exactly reconstruct my nonlinear dynamics, which is really remarkable. So this has been kind of the promise and the hope of Koopman all along, is that for nonlinear dynamical systems, I can find some compact linear representation that allows me to follow trajectories of the nonlinear system using linear analysis, which is really cool. Now, what I'm going to show you is that to do this exactly, so that this y dot, y3 dot equals a function of these y1s, y2s, and y3s, there's only a very few types of systems where this is even possible, right? So this is not something that you can universally do for any nonlinear differential equation. I'll show you some examples of where it fails. But when it is possible, you can do amazing things with control on this Koopman linear system. Okay? And I'm just going to make an aside that once you have this Koopman operator restricted to a Koopman invariant subspace, that's a fancy way of saying that when I write my dynamics in these variables, they're in some sense closed with those variables. I can take the left eigenvectors of this K matrix, and I can use those to find what the eigenobservable functions are for my system of interest. So here I look at my left eigenvectors xi of this k operator, and I find the eigenvectors associated with the different eigenvalues mu and lambda and 2 mu, and I get these invariant, these Koopman invariant eigenfunctions, okay, eigenobservable functions. So in another video, we're actually going to write the code to simulate this surface, and we're going to kind of rotate it around in MATLAB. But for now, I just wanted to kind of introduce you to this nonlinear dynamical system and how you can exactly represent these nonlinear dynamics with a linear dynamical system on these nonlinear observable functions. Okay? And when you can do this, when there exists these closed Koopman invariant subspaces, you can do amazing things like Koopman operator optimal control. Okay, so I'm taking the same exact differential equation. It still has these linear terms, these nonlinear terms, but now I'm adding some control inputs. So I can actually actuate this x2 variable with u. My Koopman linear system with inputs has the same Koopman operator k, and the inputs still only enter this second variable y2. And what's really neat about this is that, for now I can assume that I have unstable mu or unstable lambda or whatever you like. It could be stable or unstable. And now I can start doing really interesting things. Like I can actually apply LQR to this Koopman linear system. Okay, so I could have an LQR cost function where I penalize deviations of my state x from 0. So I'm going to try to stabilize the system to 0. And I also want to jointly weight control expenditure. So I don't want to spend too much control input u to get my state to 0. And so what I'm trying to do is minimize this cost function j with a choice of a controller. Okay, and usually our controller looks like u equals minus some matrix k times our vector x. This k is a controller. It's not my Koopman operator. This is probably bad notation. Let's call it this k tilde. And so instead of doing optimal control on this linearization, we're going to do an LQR optimal control on our Koopman linear system. So now we're going to get a controller u equals minus k times my bigger vector y of my nonlinear observations of x. And when I actually write this down, my nonlinear optimal controller has linear terms, k1 times x1, k2 times x2, like we expect with LQR. But because my third observable is nonlinear in x, my third term of my controller is nonlinear. So this is super cool. I get a nonlinear optimal controller using this linear Koopman framework. And in another video, we're going to go through the code for this, and you'll see how we actually develop this in MATLAB and actually go through the entire solution. But for here, I'm just going to show you the results. So here we see the phase portrait of x2 versus x1. The red dashed curve is my Koopman optimal controller, whereas the white curve is the LQR controller just on the naive linearization. And on the far right, you see the cost function, the integrated cost function over time. And our Koopman optimal controller has about 1/3 of the total cost to stabilize the system. So that means we get to the equilibrium more efficiently in terms of the state deviation and the control using this Koopman nonlinear controller. And so this is really neat. This is what we wanted all along. We wanted to take our nonlinear dynamical system. We wanted to be able to represent it in terms of a finite dimensional linear system in terms of these observable measurements. And then we want to be able to do neat things like optimal control. So when it works, it's really powerful. And now we're going to start talking about rigorously classifying when you can or cannot get these finite dimensional exact Koopman linear systems. Okay, so we saw that for some differential equations, for some nonlinear dynamical systems, we can pick a smart choice of observable functions so that when we write our dynamics in terms of those observable measurements, we actually get a linear dynamical system that exactly represents the nonlinear dynamics and that I can use to develop better nonlinear control laws. Now, a natural question comes up: when can I do this? When do my dynamics admit these finite dimensional Koopman observable subspaces that I can use for control? Okay, so the short answer is that any eigen-observable functions of my Koopman operator will span one of these Koopman invariant subspaces. So if for some, if you have some secret knowledge of your system and you know what these eigen-observable functions are, then you can define a finite dimensional Koopman invariant subspace, and you can write down the dynamics on those observables in a linear system. Now, figuring out what those eigen-observable functions are is very challenging sometimes. It's not clear. And what we find is that we don't just want to advance these eigen-observable functions in a linear fashion. What we would really like to be able to do is have this Koopman invariant subspace also include linear measurements of my state x, so I can not only advance these measurements of x, but I can also advance the state itself. And this is really important because if I want to develop an optimal controller where I'm penalizing deviation of x, then I need to know what x is doing. And ideally I would do this in a linear framework, so I can use LQR or H-infinity controllers. So to advance the state x, we have to be able to represent the dynamics f in the span of our observable subspace. Okay? And what that means is we have this invariant subspace spanned by these measurement functions ys1, ys2, all the way up to ysm. I have m of them. And I have to be able to represent all of my right-hand side dynamics in terms of those observable directions, or those observable functions, so that I can hope to write my Koopman system like this. Okay? So to be able to advance my state, right, the first n of these observable measurements are my state, I have to be able to represent my nonlinear dynamics in terms of these in terms of these subspace directions. But it's unclear if I do that, can I then get closure on the remaining nonlinear observable functions? So remember in the example before, we had this y3 equals x1 squared. And we needed this nonlinear function to represent the right-hand side dynamics in terms, linearly in terms of this y3. But we might have just gotten lucky when we had ddt of y3 equals 2 mu y3. So the fact that this was closed and that the derivative of y3 was also in this subspace, that might have been a fluke. That might not be possible for just any old system. And so what we found after thinking about this for a while is a couple of heuristics that tell you when it is or is not possible to find these exact Koopman invariant subspaces that do in fact capture the state dynamics x as well. And the realization is this: you can't have a differential equation, a dynamical system that has multiple fixed points or some kind of a periodic orbit or a more complicated attractor like the Lorentz system. You can't have that kind of multiple attractor scenario and be able to represent those dynamics in terms of any finite dimensional linear system. Right? This is pretty straightforward. You can't represent a system with multiple fixed points in terms of a linear system that only has a single fixed point. And that's because these can't be topologically conjugate. You can't do some kind of continuous deformation of the flow of my nonlinear system with multiple fixed points into the flow of a linear system with a single fixed point. And so this is a little bit disappointing. What this tells us is that if I have a system that has 3 fixed points or 2 fixed points or a strange attractor, chances are I'm not going to be able to get a finite dimensional Koopman invariant subspace that also includes linear measurements of my state x. But this is kind of to be expected, right? We're trading out nonlinear dynamics for an infinite dimensional Koopman operator. And if our dynamics are really non-trivial, then we really do rely on the infinite dimensional nature of this Koopman operator. Okay? So I'm going to show you some examples of where this breaks down pretty significantly. A really nice system to illustrate this on is this logistic map. Okay, so it's not possible to represent a system with multiple fixed points with any finite dimensional linear system. There just can't be topologically conjugate. You can't smoothly deform one into the other. And so we're going to work this out on this very simple logistic map example. Okay, so if I was going to advance my state using a finite dimensional Koopman subspace, then I would have to have any nonlinear function in my dynamics has to be in my observable subspace. Okay? And so a candidate observable subspace would be having yk be xk and xk squared. This is a typo. This should be squared, x squared at time k. So my candidate observables are my state x and the square of my state x at time k. But if I go through this same step and I say, can I represent my second observable function at time k plus 1 in terms of just these two observables, I need higher terms. So let's try this out. We're gonna take x squared at k plus 1, and that's essentially this right-hand side expression squared. It's xk plus 1 squared. And right off the bat, you see that I get xk to the fourth terms. So if I'm going to include x squareds in my observable subspace, I also have to include x to the fourths. And if I'm going to include x to the fourth, then I also need to include x to the eighths, and so on and so forth. So you get this cascade of complexity where if I'm going to include these nonlinear functions, these nonlinear observable functions of my state, then I need higher and higher order terms for these to be closed. And so this is a very simple example where you really do need an infinite dimensional Koopman operator to possibly represent these chaotic, these rich chaotic dynamics. Now that's not to say that there aren't some special Koopman eigenobservable functions that you could use to represent the system in a finite dimensional subspace. But those observable functions are not going to include linear measurements of our state. They're not going to allow us to advance x itself. And we also have no way of determining what those eigenobservable functions are. And there's just some interesting kind of math properties here that you notice that each of these rows in my Koopman operator are shifted rows of Pascal's triangle times higher and higher powers of this parameter r. So you get some beautiful structure when you start expanding out interesting nonlinear differential equations in terms of this. You pick a basis for Hilbert space, and then you expand out your Koopman operator, and you see some beautiful patterns. And I encourage you to try this on, just name an interesting dynamical system and start playing around with it. And you can also see what happens if I truncate this. Let's say I only keep the first 5 of these variables, and I just chop this off into a 5 by 5 matrix. It turns out for these very chaotic systems, you don't get very good predictive value for many iterations. And I was unable to find any good approximations to these dynamics using a finite dimensional linear system. So that's still an open problem, but based on our understanding that you can't have the same flow topology of a nonlinear system with multiple fixed points in a finite dimensional linear system, there might not be a nice closed form solution to this. But there are some cases where this actually works better than others. The logistic map is particularly nasty, super chaotic. Here's a simpler system. This is an ODE with a single isolated fixed point, so that's good. But it has finite time blow up, right? X dot equals x squared will blow up to infinity in a finite time. And if you write out the Koopman expansion, you'll see that if I pick these various functions, x, x squared, x cubed, x fourth, and so on, then my Koopman operator actually has a very, very simple structure, this off-diagonal increasing 1, 2, 3, 4, et cetera, et cetera. And you can work through this yourself just by computing, like, let's say I wanted to compute ddt of y3, right? And y3 is x cubed, so that's ddt is 3x squared x dot. Well, x dot equals x squared, so this equals 3x to the fourth. And that's why I get this 3 times y4, or x to the fourth. So easy to compute these for simple systems of your own choosing. You could also try a different basis. Instead of polynomials, you could try sines and things like that. And what we find is that for this system, even though there's no exact finite dimensional Koopman subspace that also includes x, there are ways to truncate this where you get better and better approximations of your full system. So here's a MATLAB simulation. The white curve is my full system for some time. And these different colored lines essentially show what happens when I take the first 1 by 1 subblock, or 2 by 2, or 3 by 3, or 4 by 4. And as I increase the rank of my Koopman linear approximation, I actually do get better and better agreement with my full system. So this is promising, even for systems that are a little bit nasty, where there aren't these exact Koopman invariant subspaces of finite dimension that include the state. You can still do approximation. Okay, so this has been kind of a fast overview of how we can look at nonlinear dynamical systems in terms of these finite dimensional Koopman observable subspaces. In particular, we want subspaces that include the state itself, because then we get a linear system that walks our state, that evolves our state. And if we can find that, then we can do some really neat optimal control on this Koopman linear system. But alas, you are trading nonlinear dynamics on a finite dimensional state space for infinite dimensional linear dynamics with the Koopman framework. And so we found that in lots of circumstances, you just can't get these exact Koopman invariant subspaces. But that doesn't mean you can't approximate them, and you can't do truncation, and you can't do control. So there's tons of interesting areas to keep going and keep looking in this framework. And we just wanted to share this with you. If you're interested, you can read more on the archive. Here are my co-authors, and we'd be happy to talk over email or in person about this. Thank you.